Okay, good afternoon. Today we are having the next lecture in general physics, thermodynamics and molecular physics, and the topic of today's lecture would be phase transitions. Phase transitions. Well, but first I would like to give some plan for today's lecture and seminar. The lecture today will be somewhat easier than the previous one, because the previous one was heavily mathematic. Today we are going to touch some real physics. While, well, mathematical part would be here, but nonetheless it would be pretty much better than the previous one. But about the seminar today would be, I think, one of the most challenging seminars ever of our course, because we are going to solve a single problem, but that single problem would have almost all of the tricks which you might need or might not need in your life about thermodynamic potentials. Okay, I would like to start with the description of phase transitions, which is on the level of the high school. So basically, I think you know that there are different phases of matter which have different properties. And the best way to describe those properties is not thermodynamical way, but through describing the properties or arrangement of different molecules in these phases. For example, we have gas phase. Gas is usually a low density. You have low density of molecules which are arranged in space chaotically, and relatively the energy of interaction is much less than the kinetic energy of those molecules. Okay, this is E int, is energy of interaction between different molecules, while Ek is the kinetic energy. So mostly in gas, the energy is stored in the kinetic form, and there is almost no interaction, since the distance between the molecules is so high that no interaction can happen, almost. Slightly different phase is liquid phase. Oops. Wow. Let's say liquid phase. And in the liquid phase, the average distance between molecules is quite small. So all of those molecules are pretty much packed. But nevertheless, the arrangement of those molecules is still chaotic, but the energy of interaction is approximately of the same order as the kinetic energy. And since, nevertheless, these molecules can pretty much freely move, that's why in a liquid phase, while the volume is approximately constant, it's very difficult to change because all of those molecules are already packed tightly. So you can't change the volume of this liquid, but nevertheless, you can change the shape. Shape can be changed easily. So your liquid phase can easily be reshaped. While for the gas phase, you can easily change volume and shape. So at least this description quite conforms with intuition. So In gas, easily changing volume and shape. In liquid phase, you can change the shape, but can't change the volume. Pretty much different phase is solid phase. Solid. In a solid phase, molecules are not only packed, but they are also arranged orderly. So in solids, you have this crystalline structure. Crystalline structure. And also, this arrangement is called crystal lattice. In the solid phase, it is both difficult to change the volume and to change shape. So shape is almost fixed. So of course, there is an exception to that. You know that all of the solid objects can be deformed, but usually those deformations are quite small. So these are three main phases. Sometimes fourth phase is being introduced, which is called plasma. It's not going to be the topic of our lecture course, but nonetheless, I think you should know that if you heat up the gas to such a large temperature that the collisions of the molecules lead to the decay of these molecules into positively charged ions and negatively charged electrons, so then this state is called plasma. So in the plasma state, you no longer have molecules actually, because the collisions between molecules are so strong that usually a couple of electrons are being withdrawn from either molecule, and that leads to the appearance of the electric charge. So altogether in plasma form, you have positively and negatively charged particles. And well, the most convenient example for plasma, which you probably have, everyone has seen, is flame. So in the flame, you have this structure, and these things which glow in orange or blue, they are charged particles. So this is plasma, one of the examples of it. Okay, so for now I'm going to say something which will not surprise you, that actually the same kind of matter can be found in different phases, depending on the external conditions. So for example, I think you are most convenient with water. Water can be evaporated, and water can be converted into solid phase, which is called ice. Any questions, please? Crystal lattice, yes. Lattice. Okay. So the actual state in which the matter can be found depends on the external conditions. And sometimes both of these phases, or even three of them, can be found at the same time in a state of equilibrium between phases. So the goal of thermodynamics with respect to these phase transitions is to describe thermodynamically these phase transitions. So let's first of all name those transitions for our convenience. So let's say we have gas, a liquid, and solid phases. Okay. So when I go, the most simple one, when I go from the liquid phase to the gas phase, how it's called? Evaporation. And when I go in the reciprocal direction? condensation. Okay, so but when I go from the solid phase to the liquid phase, that is, oh, well, I couldn't recognize, but I mean melting. And in this direction, freezing. That's freezing. Okay, and finally, this one, this is the term when the solid phase goes into the gas phase, it's sublimation, yes. So I think mostly when people use the term sublimation, it's related to psychology. Like something you have some kind of a desire, but you sublimate them into some other activities. And the opposite direction. Inverse sublimation. Inverse sublimation, sometimes it's called deposition. Deposition. Deposition is often a technological process which is now more used in nanotechnology. So when you want to grow a perfect crystal structure, then you employ one of these processes which is sometimes called liquid phase deposition or chemical vapor deposition. So the final result of this is that you have some kind of a gas, and then you apply some pressure, you make conditions which favor the formation of the crystal structure. And using this process, you can grow very thin layers of crystal structures, and in a highly controllable way. And most importantly, you grow crystal structure with atomic precision. So you grow on some kind of a substrate, you can grow in the process of sublimation a certain number of layers of some crystal structure with perfectly arranged atoms. Yes?
How would you call one of these phases?
Ionization, probably. Don't know. So let's say we go from gas phase into plasma. Yeah, I think this ionization. I don't know the name actually for the reciprocal process. when the plasma particles are condensed into neutral molecules, so probably, I don't know. This is ionization. Okay, so this is it, and the most peculiar feature about these phase transitions that usually to make a phase transition you need to apply some heat. For example, if you want to evaporate liquid, you need to heat it up. So you need to supply heat to the liquid in order to make it into the gas phase. Since mostly phase transitions in our practical environment happens at the constant pressure, this heat, heat of vaporization, for example, is equal to the difference between specific enthalpy of the gas phase minus specific enthalpy of liquid phase. By specific enthalpy, I mean, for example, enthalpy divided by the mass of that gas. So, of course, enthalpy is the additive quantity. So if you have twice the amount of gas, then you have twice the amount of enthalpy. That's why I can introduce a specific enthalpy quantity. And this specific heat of evaporation or vaporization is the difference between specific enthalpies of both of these phases. And also, in addition to these changes, you not only have the change in the enthalpy, you also have the change in entropy. So I can also introduce some specific entropy of gas phase and specific entropy of liquid phase. Okay. And again, this lambda here is temperature times the change in the specific entropy. Okay. And any of such processes accompanied with this heat, sometimes it is called hidden heat. So like you kind of release or well, you kind of release some hidden energy in the particles. So when you go, for example, from gas phase to the liquid phase, then heat is being released, and that happens because the energy of the interaction between particles in liquid is negative, because mostly neutral molecules are attracted to each other. So when the distance is not so very small, they are attracted. Of course, when you go beyond some very small distance, they are repulsed. But usually, so in here, you change the distance between molecules from large to some close distance. That's why this attracting force makes some positive work. And for this reason, when you go from gas phase to the liquid phase, typically heat is being released. Okay. Now, the next situation I'm going to consider is the following. I will concentrate now on the transitions between gas and liquid phase, because both of these phases are very simple to describe. They can be described by the density. So let's say you have a vessel with a piston, and you can freely change the volume of the vessel. And initially, you have quite a small amount of gas, which is sparsely distributed over the vessel. So the volume is quite large here. And now you are going to push the piston down and decrease the volume available for the gas. And let's assume that all of this happens at the constant temperature. So what will happen? You would be able to decrease volume to some extent. And with the decrease of volume at a constant temperature, the pressure of the gas would increase until it reaches some threshold value, which is called saturated vapor pressure. PS. So you wouldn't be able to increase the pressure of the gas beyond the saturated pressure level. So in here, in the initial condition, you have pressure of gas less than the saturated vapor pressure, but as you decrease the volume available for the gas, you increase the pressure until it reaches the saturated vapor pressure level. And from this point, condensation onsets. So the condensation starts, and as you try to decrease the volume further, instead of the pressure increase, the pressure would remain constant. But what you would have, the part of the gas would go into the liquid phase, because usually the density of liquid is much smaller than density of the gas phase. And for this reason, once you decrease the volume available for the gas, it becomes inevitable that some of the gas transforms into the liquid. But the pressure remains the same. You have the same saturated vapor pressure. And this process will continue until you transform all of the gas into the liquid phase. So now, in the final state, you have all of the matter in the liquid phase. But as you want to continue to further decrease the volume of available for this liquid, the pressure would start increasing beyond the saturated vapor pressure, and the increase would be very sharp because liquid is hard to compress. So if I present this on the PV diagram, so I start from somewhere here at a very small P0 pressure at some volume, and I decrease volume until I reach PS, saturated vapor pressure. Then the pressure would remain constant until I transform all of the matter into the liquid phase, and then there would be the sharp rise in the pressure as I want to decrease the volume even further. So this is the isotherm of typical real gas, how it looks like. So this, instead of this PV equal to the constant, which you have been familiar for the ideal gas, real gas, which are capable of condensation, they have this kind of an isotherm. Okay, so now let's continue. Let's continue further. So as you see, for each temperature, so this saturated vapor pressure is actually a function of temperature. It's actually the function of temperature. So I can build these kind of isotherms by repeating the same experiment at different temperatures. So what I would see the following. That as I increase the temperature, the length of this, or actually, yes, the length of this plateau would decrease as I increase the temperature. So in here, this is the direction of the temperature rise. And the length of this phase transition would decrease as I increase the temperature until the phase transition disappears. And this point where the phase transition disappears is called critical point. So there is some volume, pressure, and temperature associated with the critical point. Critical point, which is described by critical pressure, critical volume, and critical temperature. So if I increase the temperature of the gas beyond the critical point, then the gas-liquid phase transition wouldn't happen. So beyond the critical point, I would have this type of a smooth curve on a PV diagram for the isotherm. Usually, when phase transitions are being studied, these phase transitions can be plotted on a so-called PT diagram, because as you see, there is a function of saturated vapor pressure, a function of temperature. So that means that pressure and temperature seem to be the most important external conditions for the phase transition. So you can describe all of the phases by pressures and temperatures. Okay, let's say here goes the pressure, here goes the temperature. P critical, V critical, critical temperature. And then we need to decrease. Okay, so let's start with this. Let's try to build this PT diagram for the phase transition, and for water. So let's start with the pressure of 1 atmosphere, and we know that for water at 1 atmosphere, so at normal conditions, the boiling point of water is at 373 kelvins. So beyond here, you have gas phase. And when you go from this to 0 degrees Celsius, which is 273 Kelvin, you have liquid phase. But beyond that, below this temperature, you have a solid phase, so you have ice. And let's say we decrease this pressure. As I decrease, the saturated vapor pressure would decrease. For some reason, actually, the temperature at which the melting happens increases slightly, and until these two curves meet at so-called triple point. And below, at pressures beyond the triple point, so below the triple point, you would only have gas and solid states. So to the right of here, so let me, for example, here, this is the gas phase. Oops. So in here, you have gas phase. In here, you have a liquid phase. And in here, you have solid phase. In fact, there can be multiple solid phases. So, for example, you can form a different type of the crystal structure depending on the conditions, but I think that would be quite beyond the topic of our today's lecture. And the most important part that at some temperature, when you reach the critical temperature and critical pressure, this curve, which separates gas phase from the liquid phase, disappears. So this is the final point here. And here is the so-called critical point. So it looks, at first, it looks like impossible, but there is no difference between gas and liquid phase beyond the critical point. So this is the critical point. Well, now what we need to do is to develop some kind of a thermodynamic theory which would allow us to describe all of these phase transformations and determine the shape of curves at which we have the equilibrium between two different phases. So when you are located in your conditions at some of those regions, then you would have a single phase, either solid, liquid, or gas phase. But when you are located on this curve, for example, you have an equilibrium between gas phase and liquid phase. So that means that both of those phases can be present simultaneously. And when you are located here, that means that you have an equilibrium between solid and liquid phase. So again, you can have, like, for example, ice covered by water, and both of them at equilibrium with each other. And at the triple point, you may have gas, water, and ice in the equilibrium with each other. And usually, actually, when Kelvin's temperature scale is concerned, usually this temperature scale is calibrated with respect to the triple point, which is easily reproducible. As you see, if I want to, for example, determine this point, yes, so let's say at 1 atmosphere, the temperature of the melting point of ice is 273.15 kelvins. But this temperature is subjected to fluctuations, which happen with the fluctuations of the external pressure. So this point is not strongly determined. And it's quite inconvenient to reach this point at the experiment because you need to control pressure. But pressure itself is a fluctuation quantity. So that's why it is quite inconvenient to have this point as as one of the main points of the Kelvin temperature scale. But in here, when you have three phases in equilibrium with each other, this point is not easy to miss. So once you have only two of them instead of three, then you are out of the triple point. So usually the Kelvin temperature scale is determined by the condition that the temperature at the triple point is 273.16 Kelvin. So it's actually, I have over-exaggerated curve here. So this curve is almost vertical here. And the triple point is only 1/100th Kelvin to the right from this point. And also, here go some important quantities here. For the triple point, the pressure is 610 pascals, which is a very small fraction of the atmospheric pressure. And temperature is 273.16 Kelvin. While for the critical point of water, pressure equals 22.1 megapascals. So that means 221 atmospheres. That's really a huge pressure you need to achieve the critical point. And the temperature is 447.3 kelvins. So that's why it's almost impossible to observe the critical point in nature, because you can't achieve this kind of a high pressure and this kind of a very high temperature naturally. Probably you can do this, for example, inside some volcanoes or something like this. But it is much easier to achieve in laboratory conditions, when you can have a very small capsule which contains water, and you can increase the pressure and temperature there almost infinitely. Any question?
The critical point, the temperature.
647.3. And in here, 22.1 megapascals. Yeah.
Why to increase the temperature, the phase is decreasing?
Well, that would be explained further when we will study the next part of this lecture about the Clapeyron-Clausius equation, which describes the form of these curves. And from that, we would see how this pressure increases as I increase the temperature. So that actually happens, and you can consider that at this stage, you can consider this as experimental observation. It was observed in such a way that as you increase the temperature, the length of that phase transformation part decreases. But I think more convenient explanation would be given on the next lecture when we would study van der Waals gas model. And in a van der Waals model, you would see by yourself how it actually happens and what determines the shortage or the shrinking of this phase transformation part.
And this is volume pressure.
here P critical, V critical, in the curve, pressure volume. So this is pressure volume at the curve at above the critical temperature. So in here, you would not have a horizontal part at all. So you, at any point, as you decrease the volume of the gas, or whatever it is, this is like supercritical liquid sometimes, or supercritical gas phase. So when you decrease the volume, actually the pressure continues to increase without any phase transformation at all. So no phase transformation happens. So actually that means that you are able to avoid the phase transformation. Let's say, for example, you start from here, then you go in this direction, and you can go to the other side of this curve without any phase transformation at all. So that's the most peculiar part. So without this hidden heat and whatever else. So there is such an ability to transform the gas into the liquid phase without this phase transformation, just by going around the critical point. Okay, so now goes the theory of all of this. Now it's going to get slightly more complicated. So I suggest to make a 5-minute break before we start with the more complicated part of the lecture today.
Could you explain about how would, for example, these phases go into plasma, for example, after the critical point, what happens?
After the critical point. So when you go somewhere beyond probably here, let's say, I don't know the actual form of this curve, like you go somewhere here, for example, at 2 or 1,500 kelvins or something more, the kinetic energy of the gas particles becomes so large that it goes into the plasma. Well, I'm not ready to say that whether there would be any kind of a hidden heat released when in the transformation from the gas to the plasma state. But nonetheless, the state of matter would change at this point. So usually you are required to have a very large temperature to have plasma. Sometimes it can be like few thousands of kelvins. Sometimes it's even more, like a few dozen thousands of kelvins. And if we speak about the plasma from which we can harvest some energy, usually the people who study plasma physics, they have a specific goal in mind. So the interest to plasma state of matter is not purely theoretical. The reason is you need to have plasma to onset the nuclear fusion reaction. And that, if you are able to stabilize your plasma and to confine it somewhere at some point of space, you would be able to harvest energy from the fusion reaction. And that fusion reaction is similar to the fusion reaction which happens in our sun. So if you are capable of handling plasma on Earth, then you would be able to create artificial sun and make it produce energy for us to consume. But the problem is very difficult, I would say, because that plasma in which you may have this nuclear fusion reaction should be heated up to millions of kelvins. So that means that you cannot hold a plasma in any kind of a solid case. So you cannot invent a vessel to hold the plasma, because any vessel would be completely burned by the plasma of such a high temperature. It wouldn't be able to withstand it. So usually when plasma is handled, it is handled in a so-called magnetic traps. So you create a special sort of arrangement of magnetic fields to confine your plasma in a certain volume in space. But plasma is very tricky kind of matter because there are lots of instabilities in it, and it tends to escape from any kind of arrangement of magnetic fields. So that's the reason why we don't have fusion reactors so far. So I think this is about it, about plasma. Okay, I think we should start the next part of the lecture. So let's first of all look back on all of those phase transitions I have described during the previous part of the lecture. actually, these phase transitions are not the only phase transitions possible in our world. So the phase transitions actually can be of two types. So these type 1 and type 2 phase transitions. In a type 1 phase transition, you have an abrupt change in enthalpy and entropy. So in these phase transitions, you need to supply some heat in order to enforce this phase transition. But in a type 2 phase transitions, there is no abrupt change so no, I think discontinuity, no discontinuity in enthalpy or entropy. But what actually happens that in a type 2 phase transition, some kind of a ordering happens. So what I mean here, in type 2 phase transitions, okay, let me give you just some examples of type 2 phase transition. So for example, this is a transition between the ferromagnetic state to paramagnetic. Okay, ferromagnetic state, actually like ferromagnets, are the type of materials which have very strong magnetic field in them. So in a ferromagnetic state, your solid has domains which produce very strong magnetic field. So usually these domains are somewhat chaotically oriented, but it is possible to orient all of those domains in a single direction, and that would give you a magnet. But in the paramagnetic state, there are no such domains. Each molecule or each atom of the material has its own magnetic moment randomly oriented. So when you go from these random orientations to these ordered domains, then you have a type 2 phase transition. And this phase transition happens without any kind of a specific heat of ferromagnetization. So there is no such thing as specific heat of ferromagnetization. So there is no entropy change and enthalpy change when you go from this state to this state. You just acquire some kind of an order. And other types of the type 2 phase transitions which have been discovered in 20th century is a superfluid transition. In a superfluid transition, which was initially discovered in helium, when you cool down helium beyond some temperature, the liquid, the liquid turns into the superfluid, so it doesn't have any viscosity. So in a superfluid, no viscosity. So viscosity of the liquid disappears. Also, superconducting transition. So superconducting transition. When the resistivity suddenly turns into 0. So it was actually discovered that if you decrease if you plot the dependence of the resistivity of the material as a function of temperature, then it decreases, but at some point it suddenly drops to 0. So your material turns into a superconductor. This is also an example of the type 2 phase transition. there is also no discontinuity in enthalpy and entropy in between these two states, but for some reason, actually, the resistance of the wire drops to 0.
Is supposed no change in entropy?
It's
There is no change in entropy.
no change. So the yeah. So it looks like there is some kind of well, some kind of a contradiction in here. Yes. So here we have some order. Here you don't have any order state. But actually, what happens is yes, indeed, there is no change in entropy in between these two states, but there is change in molar heat capacity. So so in this state, the molar heat capacity is different from here. So when you plot the dependence of the entropy as a function of temperature, then you would see like this type of change. So you get it in one kind of dependence, and then you transform to other type of the dependence. So there is the change in entropy in the behavior of entropy, but not the discontinuity. And this ordering happens, how I would say it, somewhat continuously. So this ordering happens continuously. So as you go from this state to this state, for example, the size of domains is at the starting point is very small and then increases of the different domains as you go further into the lower temperature scale. And also these domains can be destroyed by the magnetic field, so there is also another parameter which is involved in this phase transition. So in here, although there is some order in here, indeed there is no discontinuity in entropy, but this ordering happens like continuously. So you start forming domains, but initially those domains are very small and involve a very small number of atoms. And then as the temperature decreases further, the size of those domains increases. So that's the reason actually why you don't have discontinuity in here. And in here you also like in here you see that there is a drop of the resistivity to 0, but actually the superconducting transition is associated with the formation of pairs of electrons, which are called Cooper pairs. And initially when you go, okay, viscosity means it's 0. How could viscosity of a liquid be 0? Well, it is actually very the same thing as how can the resistivity be 0? It is a very special state of the matter in which it is possible for the different types of the liquid to move with respect to each other without the loss of energy. So that is what happens when viscosity goes to 0. And in a superconducting state, the fraction of Cooper pairs to the unpaired electrons increases gradually or continuously. So above the temperature of superconducting transition, the fraction of Cooper pairs is 0. But as you go below this temperature of superconducting transition, you increase the fraction of electrons which form Cooper pairs. And this resistivity, which is 0, it is up to some critical current. So with these Cooper pairs, you can conduct only a finite amount of electric current. So as you increase the current further, then normal electrons, which are not paired, would start their motion, and that would lead to the energy dissipation and the resistivity. So these phase transitions are really tricky. Although there is ordering, there is no change in entropy. And they happen kind of seamlessly without drastic changes in the parameters. But nonetheless, there are changes in observables and quite distinct changes at that. Okay, so, but today what we are discussing actually the type 1 phase transitions. For the type 2 phase transitions, the theory was invented by Lev Landau and Ginzburg, and they have a Nobel Prize for that, because that theory of type 2 phase transitions describes superconductivity, superfluidity, and also ferromagnetic to paramagnetic transition. But it's quite complicated to be studied as a part of our course. Okay, so let's develop something, some kind of a description for the type 1 phase transitions. On the previous lecture, I have introduced thermodynamic potentials, internal energy, enthalpy, free energy, and free enthalpy, or Gibbs potential, G. And up till now, I have discussed all of these thermodynamic potentials for a fixed amount of matter. So I have assumed, for example, that amount of matter is fixed at 1 mole or at some other quantity, but it doesn't change. Okay, so now I'm going to study how these thermodynamic potentials change as they change the amount of matter. So let's go from the amount of matter actually to the number of particles involved. For example, the number of molecules. And let's assume that all of these functions, for example, u of s, v, are additionally considered the functions of the number of molecules. Okay. Actually, if you consider, for example, the differential of a single potential, so du equals to, as you know, TdS minus PdV. But if you allow the number of molecules to change, you need to add an additional term, which is proportional to the change in the number of molecules. And this thing is usually called chemical potential. It also happens that exactly this contribution is present in all of the thermodynamic potentials. Oops, I made a small mistake here. Sorry. Okay, so all of these actually change as you change the number of molecules. Actually, in thermodynamics, there are two types of quantities. One of them changes as you change the number of molecules, the other one is not. And those quantities which change as you increase the number of molecules are called extensive variables. So in here, I have all additive quantities, like internal energy and all of other thermodynamic potentials, H, F, G, volume. If I have twice the amount of gas, I would need twice the amount of volume. Entropy. Well, so far that's all. Those are extensive variables. They increase by a factor of 2 if you increase the amount of gas by a factor of 2. The other variables are called intensive variables. and they doesn't seem to change when you increase the amount of gas. For example, pressure, temperature, and now also this new quantity which is called chemical potential, they don't change as you increase the amount of gas. So if you, for example, if you have one finger and its temperature is 36 of Celsius, but if you have 5 fingers of the same temperature, the temperature of the whole system would remain 36 Celsius. So temperature is the parameter which is independent of the amount of matter. And the same goes with pressure, and the same goes with this chemical potential. So those are called intensive variables. And as you see, actually, in all of these differentials, I have a combination of the intensive and extensive quantities. So they can be paired up to form ordered pairs. Temperature is coupled to the extensive entropy. Pressure, intensive pressure, is coupled to the extensive volume, and also intensive chemical potential is coupled to the extensive number of molecules. Okay, number of molecules also goes here, of course. So now it looks like I'm making the things even more complicated. So instead of 2 variables, I have already 3 variables here. So I need to get around this, and you need to somehow wrap it up. So to understand where this chemical potential, for example, comes from. Well, let's say how all of these potentials change as I increase the number of molecules. So let's say, for example, internal energy as a function of entropy and volume and the number of molecules can be presented as n times the internal energy per single molecule. But in the internal energy per single molecule, I need to have also the entropy per single molecule and volume per single molecule. And yes, 1 molecule here. Now, the same stuff for H. Okay, SPN. What I have here, n times the enthalpy of enthalpy per single molecule. Okay, similar can be written for the free energy, and the most importantly, similarly can be done for the Gibbs energy. In the Gibbs energy is different from all of the other thermodynamic potentials because it contains is a function of the 2 intensive variables initially. So 2 canonical variables for the Gibbs energy, pressure and temperature, are both intensive. That's why I can write that Gibbs energy of n molecules, TPn, equals to n times Gibbs energy per single molecule at the same temperature, pressure, but the number of molecules equal to 1. So that means that if I calculate the derivative of Gibbs energy over the number of molecules at the constant pressure and temperature, which is by definition in here is the chemical potential, that would give me exactly Gibbs energy per single molecule. So the main meaning of this new quantity chemical potential is actually Gibbs energy per single molecule. That's why Gibbs energy is one of the fundamental thermodynamic potentials when it comes to the phase transitions or when it comes to chemical reactions. Because I can handle it in this way. So I can even write that Gibbs energy is n times mu, and mu is the function of pressure and temperature for any material. Okay. Okay, now let's consider the equilibrium between different phases of matter. So let's assume that we have a closed vessel, an isolated vessel, and in this vessel I have two different phases of matter. So I have liquid droplets and I have gas. And let's say that I have N1 molecule in the gas phase and N2 molecules in the liquid phase. From the previous lecture, you should know that equilibrium state maximizes the entropy. So S entropy is maximum. So is, okay, is maximal here. So that means that entropy, which can be presented as a function of, so let's say we have volume, we have also, volume and the number of molecules in one of the states is maximal. So that means that if I consider this entropy, then the derivative of this entropy with respect to N1 should be 0. So at each moment of time, actually what happens is that some of the molecules which are in the liquid phase escape into the gas phase, but approximately the same number of molecules from the gas phase happens to be caught in the liquid phase. So this equilibrium between two different phases is called dynamic equilibrium. It doesn't actually mean that you have a fixed amount of molecules in each of these phases. These phases exchange molecules among each other, but overall, the average number of molecules in the gas and liquid phase remains the same. Let's write the condition for equilibrium between these two phases. So let's first start with the differential for the Gibbs energy. So it says that dg is minus s dt. Okay, plus v dp plus mu dn. Okay, I think I have done something wrong here. What I actually need to determine is entropy as a function of all these variables. So let's start with the following: that du is equal to T ds minus P dV plus mu dn. So from here, I can get that ds equals to du plus P dV minus mu dn over the temperature Okay. So when I have the entropy of this mixed state, so I can write that entropy is equal to the entropy of the gas phase and entropy of the liquid phase. So let's consider this actually these two parts. So let's assume that we have an exchange between in volume and the number of particles here. So then ds over dn1, when all of the other is constant, and total internal energy actually inside this box also remains constant, because I don't have any kind of the work done on all of this system, and I don't have heat transmitted to the system as a whole. That's why I can assume that in Sg plus S liquid, these du's cancel out. So, okay, let me. Okay, well, let's just write it explicitly. So in here I have the change in Sg equal to the increment of internal energy divided by temperature of gas plus pressure of gas. And well, I can here I can write actually temperature of gas, pressure of gas divided by temperature of gas times the increment of volume of gas minus mu of the gas phase divided by temperature of the gas phase multiplied by the change of the number of molecules in the gas phase. So here it's N1. And I need to add up all of the same terms for the liquid phase. du liquid divided the temperature of the liquid phase plus pressure in the liquid phase divided by temperature of the liquid phase times dV liquid, and again minus U liquid over T liquid dN2. And what's important here in the whole of in all of this, so this is the ds of the whole system, is that first of all, sums of internal energy Ug plus Ul is constant. That's why du liquid is minus du of the gas. Also, the volume of this system is constant. That's why dV liquid equals minus dV of the gas phase. And the number of particles is also fixed. So there is no influx of external molecules. So I can write that dN in the liquid phase, this is dN2, is equal to minus dN1. And after I plug all of this into this expression for the change in entropy, I would get the following. ds equals to 1 over T gas minus 1 over T liquid times du gas plus pressure of gas over the temperature of gas minus pressure of liquid over the temperature of liquid multiplied by d volume of gas. And finally, minus mu of gas over temperature of gas minus mu of liquid over temperature of liquid multiplied by the change of the amount of molecules in the liquid in the gas phase. So now I have three components, and I can make some conclusions, because I know that entropy is maximal. So all of my variables which determine my entropy are fixed at some points where I cannot increase the entropy anymore. That means that derivative of entropy with respect to any variable here should be 0. And that means that first of all, I need to have 1 over temperature gas to be equal to 1 over temperature liquid. So that is the condition for the thermal equilibrium, as you know it. So actually, I could have postulated that initially, but in here I have the same procedure which allows you to establish the condition for thermal equilibrium in the system. And finally, also I have P gas over T gas equal to P liquid over T liquid. From here and from this follows the condition for the mechanical equilibrium, that pressure of gas should be equal to the pressure of liquid. Otherwise, I can do something to increase the entropy. So here goes the condition for mechanical equilibrium. And finally, there is another condition which is related to the equilibrium with respect to exchange of particles. And that is mu gas over T gas equals to mu liquid over T liquid. So that means that the chemical potentials in both of these phases would be the same. And this is the most important consequence, because the first two actually have been postulated even before about thermal equilibrium and mechanical equilibrium. But this one is something non-trivial here. So that's the main condition for equilibrium between different phases. And in the triple point, so for the triple point, when you have three different phases, the condition would be that chemical potential of the gas phase would be equal to the chemical potential of the liquid phase and equal to the chemical potential of solid phase. So if you have multiple phases involved, then all chemical potentials of all of those phases should be equivalent or equal to each other. And this is actually one and single equation which is needed to consider equilibrium between different phases. Now, I'm going to derive from this equation, I'm going to derive the Clapeyron-Clausius equation. So I have initially postulated that since chemical potential is determined as a Gibbs potential divided by the number of particles, then it should be the function of pressure and temperature of that phase. This is what can allow me to determine the form of the pressure-temperature equilibrium curve. So let's say, for example, we consider equilibrium between a liquid and gas phase. An equilibrium between gas and liquid phase. And there is an equilibrium curve, which is the dependence of the saturated vapor pressure as a function of temperature. So that means, so let's say, for example, I have T0 and P0, one of the points of this curve. So that means that the chemical potential of liquid at P0, T0 equals to chemical potential of gas at the same P0, T0. And now let's say I go to some other point. I make a small step. I increase slightly both the pressure to P0 plus dP and temperature to T0 plus dt. And since I remain on the same equilibrium curve, that means that chemical potentials of liquid and gas remain the same or remain equal to each other. Actually, these quantities change from initial ones, but they remain equal to each other. Okay. So now let's write the differential of this chemical potential as a function of pressure and temperature. So it says the following, that d nu should be equal to dg divided by n at the constant number of molecules n. And then I use well-known differential for the Gibbs energy. So that is minus s dt plus v dp divided by n. So that would give me minus s over n dt plus v over n dp. So in here I have entropy per single particle and volume per single particle. And that means that actually I can present it as minus, let's say, molar entropy, or let's say specific entropy for that particular phase divided by the number of molecules in 1 gram or in 1 mole. So let's say for 1 mole, an Avogadro plus molar volume, Sm and Vm over an Avogadro dP. So these two equations actually mean that d nu liquid should be equal to d nu gas. So that means that minus molar entropy of liquid, okay, here I place L as a superscript. It is not to be confused with with S to the power of L. This is another index just here for liquid. SL over M over NA times dt plus molar volume of the liquid phase over N Avogadro times dP equals to all the same for the gas phase. Molar entropy for the gas phase over N Avogadro times dt plus molar volume for the gas phase over N Avogadro times dP. And this can be considered as a linear equation in which I need to determine dP, how dP depends on dt. So I can write it as follows. dP over dt equals to S molar of liquid phase minus S molar of gas phase. Or I can actually write in the opposite way. And here I have forgotten minus. Okay, I can actually, since actually the entropy of the gas phase is actually larger than entropy of the liquid phase, so I can actually go in the other way. So let's do molar entropy of gas phase minus molar entropy of liquid phase over molar volume of gas phase minus molar volume of the liquid phase. And that's all. That's dP over dt. But we need to understand actually the change in these molar entropies. Molar entropies. To do this, we can write the following, that molar heat of evaporation, or vaporization, equals to temperature times the increment of molar entropy. That's by definition. If I need to spend this amount of heat to convert 1 mole of liquid into 1 mole of gas, that means that this is equal actually to this change. And finally, this can be written as follows. Lambda over the temperature times molar volume of gas minus molar volume of liquid. And well, I think molar quantities are not that convenient for me. Probably it is better to switch to specific quantities. So instead of a molar heat of vaporization, I would change to specific heat of vaporization. And instead of molar volume, I would change to specific volume of gas and specific volume of liquid. And specific volume is the volume for 1 kilogram of the matter. That's why specific volume is actually a reciprocal density. So I can write this as lambda over temperature, and here goes 1 over the density of gas minus 1 over the density of liquid. So this is actually the Clapeyron-Clausius equation, one of the main equations which describes the equilibrium between different phases. Here goes lambda minus, here goes the difference of volumes, or difference between specific densities. And this actually can be applied to any phase transition. It doesn't matter whether you have a transition between liquid and gas. It can also be applied to transition between solid and liquid. Let's say, for example, okay, let's see how it works, first of all. So now we have derived this equation. This is one of the main equations for the phase transitions. Clapeyron-Clausius equation. And now few examples. So as you see, the definition, the derivation of that equation is quite complicated. Do you agree with me that this derivation is kind of complicated? It starts off with a very simple stuff. I just need to demand that chemical potential should be equal. But first of all, chemical potential was only introduced today on today's lecture. So it's a new and so far, I think, vague concept to you. And well, nonetheless, we were able to get this. There is also the other way to derive this equation using the Carnot cycle. I think you might enjoy it better because it is less algebraic. I will sketch this derivation here. So we can discuss the Carnot cycle. As you know, the thermal efficiency of the Carnot cycle is independent of the working substance. So I can work on the phase transition part of our isotherms. So for the Carnot cycle, I need to have 2 isothermic processes and 2 adiabatic processes. But I can choose my isothermic processes to be that horizontal path of that phase transition curve. So I can start, for example, here at larger temperature T1, and I can have here lower temperature T2. So these parts are not involved of the isotherm. So I go from here to here. So what I do here in this part of the process is I evaporate liquid at larger temperature. Then I go into a adiabatic process, and now I slightly change the pressure here. And then I go back. So I perform a condensation of the part of the gas into the liquid phase, and then I go back here. And okay, that pressure difference and volume difference in the adiabatic process can essentially be neglected. This can essentially be neglected. So what I have here, that in the process of vaporization, I have consumed the amount of heat of lambda times here goes lambda times mass. So this is the amount of heat I have consumed in my process. But I need also to calculate the amount of work done in this cycle. And the amount of work done in this cycle is equal to the change of volume, delta V, multiplied by small change of pressure, dP, between these 2 isotherms. So essentially, it's almost a rectangle, or it's almost a parallelogram. That's why I can multiply the change of volume by the pressure difference here. And it says that dP times delta V over lambda m should be equal to temperature difference T1 minus T2 to the larger temperature T1. And from here, I can get almost the same equation. dP over dt equals to lambda m over delta V. Okay, now I need to calculate the change of volume. The change of volume is calculated as volume in the gas phase, m over rho gas, minus volume in the liquid phase. So I can calculate it by dividing mass over the density in the liquid phase. And also here goes the temperature. So in here I have lambda m, here I also have the temperature T. So everything multiplied by temperature. And as you see, after I cancel out these m's from here, I get exactly the same equation as was derived here. So this is an equivalent approach, and it might, well, I think it looks kind of easier than that previous derivation, honestly. So this is the main equation. Now I need to do a few examples. Let's start with something unusual. Let's consider the curve which separates liquid phase, or actually water, and ice. As we know, dP over dt is equal to, here goes, for example, lambda should be the specific heat of melting divided by the temperature over the difference between reciprocal densities of the phases. So here goes 1 over density of water minus 1 over density of ice. And it turns out that water is quite a specific type of matter, because the density of water, 1,000 kilogram per meter cubed, is actually larger than density of ice, which is about 900 of kilograms per meter cubed. That's why in here the denominator is negative. That's why dP over dt is negative for the transition between water and ice. At the same time, for the transition between liquid water and steam, okay, let's have a different value of the specific heat of vaporization. That would give me T1 minus rho steam minus 1 over density of water. And of course, the density of steam is much less than the density of water, so it can actually, so all of this is actually determined by the density of steam. So that would give me R over T over density of steam. So that would be positive. That's why when I start in the triple point and consider liquid to gas transitions, the specific vapor pressure, or not that specific, saturated vapor pressure grows as I increase the temperature. At the same time, as I increase the pressure, the temperature of the phase transition between, okay, here goes temperature. The temperature of phase transition between a liquid and ice actually decreases. So that leads to a number of important consequences which we make use in Olympic Games. And one of them, it enables us to well, actually, to skate on the ice. It is possible to skate on the ice due to this kind of a phenomena. The reason is the following. That when you consider the ice, and let's say you stand on the ice skates okay, that should be something rough, but whatever. If you stand here, you exert some pressure onto the ice. And as you exert the pressure onto the ice, so you go here further, but you decrease the temperature which is required for melting the ice. That's why the ice which is at your current temperature, which is at solid form, the part of that ice under the ice skate transforms into water. And due to the presence of a thin water layer between your ice skate and the ice, it is possible to glide over the ice. But if it had been the other way around, so if, for example, the density of ice was greater than the density of water, then it wouldn't happen. And you would not be able to glide on the sky. Okay, for water, it's quite simple. You go here, so the pressure increases, and well, temperature increases. Nothing interesting in here. Well, Clapeyron-Clausius equation doesn't explain you why this curve ends up here. So it doesn't explain you the existence of the critical point. You are no longer possible to get somewhere beyond that point when this specific heat of vaporization turns into 0. So at the critical point, this lambda becomes 0. And you cannot go further along this curve. Okay, I think I have given enough examples and main theoretical stuff about phase transitions, but let me do some conclusion, because we have discussed lots of interesting stuff today, but I need to wrap it out and give you some kind of a short messages to take home from our lecture. First of all, if you have multiple phases, the most important equation is that when you have multiple phases present in your system, then the chemical potential of all these phases should be equal to each other. That's the first part. The second part is that using this expression or using the Carnot theorem, it is possible to obtain Clapeyron-Clausius equation, which allows you to determine how the equilibrium curve on the pressure-temperature diagram goes on between two different phases. Okay. And, well, 3, I think it is quite important to remember how the phase diagram for water looks like, and you have a few important points of that diagram. So if I consider the pressure-temperature phase diagram for water, that would look like this. And in here, I have the point where I have equilibrium between all of the 3 phases. That is triple point. In here, I have this curve doesn't go infinitely. So it ends up at some point, which is called critical point. Okay. And in the case of water, the dependence of pressure on temperature goes in the opposite way. So as you increase the pressure, the temperature of the transition between ice and water decreases. So in here, dP over dt is negative. That's for water. For other substances, it can go in a different way. In the water, it happens because you have the density of water, density of ice lower than density of the water in the liquid phase. Okay, and also the numbers. numbers are important. So in here, when I have 1 atmosphere, then temperature here is 273.15. Temperature here is 373.15. The temperature of the triple point is 273.16. The pressure at the triple point is 610 pascals, which is much smaller than 1 atmosphere. And here goes the critical point, which has the pressure of 22.1 megapascals and the temperature of 447.3 kelvins. So probably if you become proficient in using this pressure temperature diagram, and if you are capable of understanding how isothermic process happens with gas, the stuff which I have explained at the beginning of this lecture, when you have gas in the vessel, and I gradually decrease the volume by moving the piston and achieve the following isothermic curve. Then I think you have what's required for understanding of the type 1 phase transitions. So let's have a short break, and then we start the seminar. Thank you for your attention. Okay. Now we are going to the seminar. Today, the seminar is not related to phase transitions. The seminar is one step behind the lecture, so we are now studying thermodynamic potentials in our seminar. And we have only one problem to consider today, but before I start, I would like to remind that in your homework, you have problems which require you to find thermic and caloric equations of state from canonic equation of state. Sorry, excuse me. If you have any question, please don't hesitate to ask me. No questions, okay. So let's say you have, for example, internal energy as a function of entropy and volume. So then, as you know, du equals to TdS minus PdV. And from here, I can get that the temperature is equal to du over ds at the constant volume, while pressure is minus du over dV at the constant entropy. And all of this is actually functions of entropy and volume. And from this set of equation, you can eliminate entropy. And then you are able to get, well, once you eliminate the entropy, then you would be able to get, for example, pressure as a function of volume and temperature. So that allows you to find out the thermic equation of state. And then, as one of the results here, you are able to find entropy as a function of volume and temperature. So once you have this and this, then you would be able to find also the internal energy as a function of volume and temperature. So you just substitute this entropy into here and get your desired caloric equation of state. So that's about the homework. That's just about the homework. For today's, we have a simple problem. Like, for example, when we have studied the ideal gas, as you know, the molar heat capacity of the ideal gas is considered constant within a quite large interval of temperatures and volumes. And due to the Meyer's relation, Cp minus Cv equals to the constant R, then you would say that the molar heat capacity at the constant pressure also remains constant in a broad range of conditions. So I have decided to pose the following problem. Can we go in the opposite direction? Let's assume that we have constant molar heat capacity at constant volume and constant molar heat capacity at constant pressure. Can we derive the equation of state of the ideal gas from this? Or is it only the ideal gas which can satisfy all of these conditions? So that's the question. So let's say we want to determine pressure as a function of volume and temperature for any substance which satisfies these two conditions. This is quite a long journey, and during this journey we are going to use a number of tricks. So if you are able to understand what happens by the end of this journey, then I think, I have been successful in delivering all of these tricks to you. So first, let's remember that during the lecture, I have shown that actually there is a relationship between the caloric and thermic equation of state. So I have arrived to the following condition, or to the following statement, that if I know the internal energy as a function of temperature at some volume V0, so if I know this only on this line, U as a function of V0 and temperature, then I can determine internal energy everywhere if I know the equation of state. So during the lecture, I have expressed the derivative of internal energy over volume at a constant temperature as a function of pressure, volume, and temperature, and relationships between them. And as I know, if I know this derivative, then I can take off from any point here and go in this direction up to any other point at any other volume and temperature and calculate the internal energy at that volume and temperature. U as a function of V and T as U of V0 and T, which is given, plus this kind of a function integrated from V0 to V. F, function of pressure, volume, and temperature. I just don't specify this function now, because if you want to look at this function, you need to go back into your notes on the previous lecture. So in here, since Cv is constant, then I can say that for any volume V0 and temperature T, I can present my function as U of V0 T0 plus Cv times T minus T0. Or can actually, for any volume and temperature, I can write that my internal energy is some unknown function of volume plus CVT. Because by definition, Cv is du over dt at the constant volume. Okay. let's express this CV as a function of entropy. As we know, du is TdS minus PdV. That's according to the first law of thermodynamics. But if I consider du at the constant volume, this part can be discarded. So what remains here is T times ds over dt at constant volume. But then I can look how my CV changes as a function of volume. So we know that dCV over volume at the constant temperature, according to the conditions of our problem, is 0, because I have postulated that CV is constant. But from this equation, this derivative can be calculated as follows. As a mixed derivative of this entropy as a function of volume and temperature. And while it is not possible to determine ds over dt, actually we know it's Tv over T, but we know the way to determine the derivative of entropy over the volume and express it as through the thermic equation of state. So that is related to the Maxwell's relation. So let's write it. Here I go dst over dvt. That's Jacobians. And as I said on the previous lecture, that once I go from TS diagram to PV diagram, the area doesn't change. So that means that I can replace this ST as VP, and again over VT. And that gives me the derivative of pressure over the temperature at the fixed volume. Or if you can't understand this derivation based on Jacobians, you can get and find out the same Maxwell relation starting from the differential for the free energy, which is minus S dt minus PdV. And from this you can calculate second mixed derivative dt dv, and here goes dv dt. And from that you can immediately obtain that ds over dv at constant temperature equals to dp over dt at constant volume. The same result. So in here, I was able to calculate only the first derivative, so I need to get one step further. So I demand that my dCV over dV is 0. So actually, this derivative equals to T second derivative of S over dV dt, which is actually the continuation of this one. So I have just rewritten this one into this blackboard. But now I replace the S over dV by dP over dt. So what I have here, the derivative of the temperature of derivative of the temperature of the pressure at the constant volume. So this is the second derivative. So I can write that this is temperature times second derivative of pressure over the temperature at the constant volume. And this is 0. from the conditions of our problem. dV. dV. dCV over dV is 0, since our CV is constant. This equation imposes a restriction on the equation of state, or thermic equation of state, since it postulates that second derivative of pressure over the temperature at the constant volume should be 0. That's already a restriction from a single condition, that CV equals constant. So I can write that second derivative of pressure over the temperature at constant volume is 0. And from this condition, I can infer how the pressure and as a function of volume and temperature looks like. So to do this, I need to integrate. So in order to if you differentiate something over the temperature and that gives you 0, that means that the function which you differentiate, and this is what you actually differentiate over the temperature, should be constant with respect to temperature. So that means that this should be some function f of only the volume. In that case, when you calculate this partial derivative of the temperature, then you would get 0, if this is only the function of volume. Now we need to make another step, since we already know that this is constant. Then we can calculate pressure. To calculate pressure, we need to integrate it. So I have f of volume multiplied by temperature. So that needs to be a linear function of temperature. But then we also need to add an additional constant with respect to temperature. So if you calculate the derivative of this with respect to temperature, this would give you 0, but this term would give you f of v. So it looks like that in order to have this CV constant, our equation of state should have this form. But so far, this f of v and g of v can be arbitrary functions of volume. We don't have any restriction on them. So as long as pressure depends on temperature and volume in this way, with f of g being any function of volume, then CV can be constant everywhere. Now we should somehow to make use of the next condition, that Cp is also a constant. To make use of this condition, we need first to establish a generalized Myers relation for any medium. So let's calculate the difference between Cp and Cv. If Cp is constant and Cv is constant, then this difference should also be constant. But of course, since we no longer have ideal gas, or we don't know what kind of a substance we are dealing with and what kind of an equation of state it has, then we don't know what Cp minus Cv is. So we need to somehow derive the difference Cp minus Cv for any kind of a substance, not only for ideal gas. So what we derive should be called generalized Myers relation. So let's derive the difference between Cp and Cv. In order to do this, we need to consider the isobaric process. So let's say that pressure is constant. And we consider this process. So it says that Cp should be delta Q over dt at constant pressure. According to the first law of thermodynamics, delta Q is TdS, so that is T ds over dt at constant pressure. ds over dt at constant pressure. Okay, but according to the first law of thermodynamics, I can write it as follows. So that should be change of internal energy at the constant pressure plus P dV, also at the constant pressure, over dt at constant pressure. Okay, so okay, this one actually depends only on the thermic equation of state. So I will left this as is, and I wouldn't do anything to this part of the equation. But what I need to find is du at the constant pressure. And I know that internal energy in my problem is the function of volume and temperature. So du should be du over dv at the constant temperature times dv plus du over dt at the constant volume times dt. If I want to calculate it at the constant pressure, so I need to add these abbreviations here, that all of these dv and dt are considered at the constant temperature. Now looking back on this one, I see that this is actually the molar heat capacity at constant volume. This is Cv, du over dt at the constant volume. While this one I have already derived during the previous lecture. So let's go back to the, okay, I need to remember this one, that pressure is f of vt plus g of v. So let me write it here, that pressure as a function of volume and temperature is f of v times t plus some g of v. So that's the conclusion of the previous part. But now I need to determine du over dv at constant temperature. So that is T ds over dv at constant temperature. And then using the very same Maxwell relation, ds over dv at t, that would give you dp over dt at constant volume. T ds over, yeah, so that's correct. So now I go back to this condition and insert this relationship. So that would give me that du at constant pressure is T times dp over dt at constant volume times dv at constant pressure plus Cv times dt at constant pressure. And now I insert it into this equation. So I can determine Cp from here. Cp is okay, Cv dTp plus T dp over dt. So now it's just a straightforward algebra. So I just insert one expression into another expression. And also I remember that also I need to add up some work, P dV at constant pressure over dTp. So that would lead me to Cv plus T dp over dt at constant volume times dV over dt at constant pressure plus P dV over dt at constant pressure. Wow, quite large actually, I would say. Good. So all of this should be constant in order for Cp minus in order for Cp to be constant as well as Cv. So, and let's now use this expression of pressure as a function of volume and temperature and insert it into this one. So as you see, it has a derivative of pressure over temperature at the constant volume. So that would give you f of v. But we also have these two derivatives which contain volume as a function of temperature and pressure. So we need to get some kind of a workaround with this one. Now let me check if I have done everything correctly. I think everything is quite okay in here. So let's go in this direction. So what we need to know is dV over dt at constant pressure. When we know only pressure as a function of volume and temperature. So let's write here, dP is actually equal to dP over dV at constant temperature times dV plus a dP over dt at the constant volume times dt. I can even insert that one into here. So, well, that would give me derivative of f times t plus derivative of g prime times dV plus derivative over temperature is f of v times dt. So if I assume that pressure remains constant, then I need to take this to be equal to 0. And then I can write that these are differentials at constant pressure. So that would give me dV over dt at constant pressure as minus, okay, that would be dV at constant pressure over dt at constant pressure. So that would give me minus f of v over f prime of v times t plus g prime of v. So now we know it, and now we can plug it into this one. Well, that would be quite complicated. Let's write it again here. That Cp is Cv plus T times dP over dt V plus pressure times dV over dt at constant pressure. It starts looking quite ugly because, well, I don't know whether we would be able to arrive to the final equation or not, but it gets like quite more complicated more and more. But let's nevertheless try to make it to the end. And I also need the previous result about pressure as a function of volume and temperature, that this is f of v times temperature plus some g of v. So let's get to the next. Let's get to the next part of this. So now let's plug in. So here goes Cp minus Cv equals to temperature times dP over dt at constant volume. That would give you F of V. Temperature times F of V plus temperature times F of V plus pressure again. And all of that multiplied by dV over dt at constant pressure. So that would give you times minus F of V over F prime of V T plus G prime of V. Okay, now it's perfectly good. It's quite long, but well. Now it's here. So let's replace that pressure by these functions f of v and t. So altogether we have the following, that this is minus f of v times 2 times f of v times t plus g of v divided by f prime of v t plus g prime of v. In here, I again assume that this f prime and g prime are just the derivatives of the functions f of v and g of v over the volume. So the equation says the following, that 2f squared of v times t plus f of v g of v is equal to minus Cp minus Cv times f prime of v. Wow, that's really difficult. F prime of v times temperature plus g prime of v. Now I think this one is epitome of what you can think of an unsolvable equation, because it's long and well, it's quite difficult to make something out of it. But nonetheless, as you see here, in the left-hand side and right-hand side, I have functions which are linear with respect to temperature. And these two functions are equal to each other when I assume the following, that when the coefficients before the temperature are equal to each other, and when the free coefficients here are also equal to each other. So that gives me two equations. The first one is 2f squared of v equals to minus Cp minus Cv times f prime of v. That's the first equation. And the second equation is f of v times g of v should be equal to minus Cp minus Cv g prime of v. I think we should start with the first one, because it contains only one function f of v. It doesn't contain g of v. While the second one, from the second one, we can try to determine g of v when we already know f of v. And now again, I write here that pressure as a function of volume and temperature equals to f of v t plus g of v. So that's essentially where we are going to. So actually, the first one, it can be written in the form like this. 2f squared equals to minus Cp minus Cv times df over dv. And that is actually the type of the equation which you all should be now familiar with. This is equation with separable variables. So I can separate the variables. In here I have variable f and I have variable v. So I can separate it and say that 2 times dv equals to minus Cp minus Cv times df over f squared. And after that, I do the integration. The integration goes as follows, that two volume plus some constant, so let's say V0, or I can write that 2 times V minus V0. Let me go here. Two times V minus V0 equals to now Cp minus Cv. And here goes 1 over f of V minus 1 over f of V0. So now I was able to determine my function f of V. Okay, here goes plus. So I can write that 1 over f of V for at any volume is equal to f 1 over f of V0, which is some constant, plus two multiplied by V minus V0 over Cp minus Cv. Okay, here goes one constant, here goes another constant, 2V0 minus Cp minus Cv. So that I can combine these two constants into a single one. So I can write that this is actually 2V over Cp minus Cv plus, okay, let's say constant K, which combines together 1 over V0 minus 2V0 over Cp minus Cv. That's a constant. Okay, so I have determined 1 over f of V, and that's already a progress. So now I can start solving the second equation. I will write here the main pressure as a function of volume and temperature as f of V times T plus G of V. And the second equation, f of V times G of V equals to minus Cp minus Cv times G prime of V. Okay, let's go to the next blackboard. That's a very long problem. So now we have the following. That I can take this f of V to the right-hand side here. That would transform me from f of V to 1 over f of V, which I have in this equation. So I can write that G of V equals to minus Cp minus Cv times G prime of V times 2V over Cp minus Cv plus constant K. Okay, that is it. We are already quite close to the final. So after I open all of these brackets, that would give me that this is minus G prime of V times 2V plus K times Cp minus Cv. Good. So now again, I'm going to solve this equation by separating variables. So I can write it here as g equals minus dg over dv times 2v plus k cp minus cv. Good. So in order to fully separate these two variables, I need to take dv to the left-hand side and g to the right-hand side of the equation. That would give me dv over 2v plus k cp minus cv equals to minus dg over g. Okay. So now I'm integrating that, and that would give me that g equals to g0 times logarithm of well, 2v plus k times cp minus cv over some 2v0 plus k times cp minus cv. So that gives me the equation for g. So now I know f of v and g of v, and then finally I am able to collect all of them in a single equation, but it feels like I have done some mistake somewhere. Let me check it. Okay, let me go backwards to where I have derived the generalized Myers relation. This one. Let me compare with my notes. There's some kind of a difference here. Yeah. For some reason, in my generalized relation in my notes, there is no p here. Let me see where the difference comes from. Let me see where the difference comes from. du plus p dv. Okay, now I get it. Indeed, there should be no p here. Excuse me for making this grave mistake, because I was able to finally do something out of this, but I have done the mistake in the course. And let me show you where it has crawled into my problem. du TDS is du plus PdV, and du goes du over dt gives you CFP, but du over dV at the constant temperature is probably calculated wrongly. Yes. Okay. To correct the mistake, let me once again derive generalized Myers relation, and now without any mistakes. So starting from here, I go to T ds over dt T ds over dt at the constant pressure. So let's not go to any kinds of internal energies. Let's just calculate it at the constant pressure. So it says that ds as a function of volume and temperature would have the following differential: ds over dv at the constant temperature times dv plus ds over dt at the constant volume times dt, and all of that at the constant pressure. So once I do these calculations, this one, ds over dt at the constant volume, is actually related to CV. So CV is actually T times ds over dt at constant volume. So this one is actually CV over T. But for this one, I use Maxwell's relation and use that ds over dv at constant temperature is dp over dt at constant volume. So in the end, I get the following, that ds at constant pressure is dp over dt at constant volume times dv at constant pressure plus CV over T times dt at constant pressure. And after I get from this one into this one, that would give me that Cp equals to Cv plus T dp over dt at constant volume times dv over, again, this is over dt, so that dv over dt now at constant pressure. So this is the real generalized Myers relation. So without any kinds of a pressure inside it. And this one is preserved. This one is the new equation. So let's continue our derivation from this point. So now I have derived the corrected Myers relation. And also I have that pressure is F of V times T plus G of V. Good. Okay, let's go back here. So once again, we need to derive dV over dt at constant pressure. Assuming that we know the function of the pressure as a function of volume and temperature. So actually, I can do it in the following way. So this is d. Okay, that should be dp over dt at constant volume over dp over dv at constant temperature. So as I have said previously, if we have these three functions, I can get from one derivative to another. But when I make these operations with these partial derivatives, I need to make sure that once I combine them into this kind of an expression, I need to add -1. That follows from this famous dA over dB at constant C times dB over dC at constant A times dC over dA at constant B equals to -1. So when I do these operations, I need to add -1 here. So now that gives me that dV over dt at constant pressure to be equal f of V over f prime of V times T plus G prime of V. Now I insert it into that equation. So I have that Cp minus Cv equals to temperature times dP over dt at constant volume. So that is f of V. And multiplied by dV over dt at constant pressure. So this is minus f of V over f prime of V t plus G prime of V. And from this point, we continue our solution. So I multiplied both sides of this equation by this denominator and get that Cp minus Cv times f prime of V t plus G prime of V equals to minus T f squared of V. Now, once again, I have I have a linear function with respect to t on the left-hand side and right-hand side. So if I want them to be equal to each other, I need to make sure that the coefficients before the t coincide and the free coefficients also coincide. So that gives me again two equations. Cp minus Cv times f prime of v equals to minus t f squared of v. And finally, Cp minus Cv times g prime of v equals to 0. So this makes the equation, the second equation, to be the easiest one to solve. Since the derivative of g with respect to v is 0, that means that g of v is just a constant g. So it is a function which is independent of both volume and temperature. And for this one, we again use this variable separation method. So on the next one we have here. So Cp minus Cv times df over dv equals to minus tf squared. Once again, minus Cp minus Cv times df over f squared gives you dv. Now we again integrate it and find that Cp minus Cv over f is volume, okay, let's say minus V0. That should be plus arbitrary constant, so let's assume that is given as volume minus V0. So this constant is called minus V0. So that gives us that f as a function of volume is actually equal to Cp minus Cv over v minus V0. And now we are ready to substitute these functions f of v and g of v into the initial dependence for pressure. So pressure as a function of volume and temperature is f of v times t plus g of v. So that gives you Cp minus Cv over v minus V0 times t plus g of v. Okay, g of v is just a constant g, so I will write just a constant g. So that would give me the following equation of state: p minus g times v minus V0 equals to Cp minus Cv times t. And now it looks quite I think I can just rename this constant g into p0. So that would give me p minus p0 times v minus V0 equals to Cp minus Cv times t. So that's equation for the substance which has constant heat capacity at constant pressure, constant heat capacity at constant volume. And as you see, it's somewhat different from the equation of state for the ideal gas, because for the ideal gas, 1 mole should have equation PV equals to RT. So I can write it as PV equals to Cp minus Cv times T. So that means that my substance becomes the ideal gas if I take P0 and V0 to be equal to 0. So the most important consequence of all of this problem is that you don't need to have the ideal gas to have constant molar heat capacity at constant volume and constant pressure. So like a more generalized family of materials can satisfy this condition. And let's make a conclusion. So I have made, again, as in the lecture, I have made lots of algebraic transformations and obtained the answer. But concluding part is that, first of all, I have made use of this Maxwell's relation that ds over dv at constant temperature is equal to dp over dt at constant volume. So this equation played, I think, the crucial role in the solution. Secondly, I was able to calculate the generalized Myers relation. So that gives me T times dP over dt at constant volume times dV over dt at constant pressure. So the most important part of this is that difference between Cp and Cv is actually determined only by thermic equation of state. And also, finally, there were these tricks about solving the equations. So by the end of this, I had the equation, for example, in the form of Cp minus Cv over dF over dV is minus Tf squared. So if you look at this for the first time, it doesn't occur to you that this equation can actually be solved, and you can determine this function f as a function of volume. So that was the crucial part of the progress. And another part of the progress was that when I determined the second derivative of pressure over the temperature squared over the constant volume is 0, I was able to get from here to here and then here. So that really looks like the solution of a simple or ordinary differential equation. Do you have differential equations now on the second year? Not yet. Yeah? So far we could solve, I think, probably the simplest equations were like the following one. Like the dx over x is, for example, some alpha minus alpha dt. So that would give you exponential dependence after you integrate it. And using the very same method, we have solved the equations in partial derivatives. So in here, but when you calculate the derivative, the thing, when you integrate the equation, the thing which is just a constant in a single variable equation becomes a function of another variable. So in here, we have derivative equal to 0. So derivative over the temperature. That means that in here you have the function of volume, not just a constant, but you have function of volume, because any function of volume is constant with respect to temperature. So this was the main part of the solution. Okay, and with this I would like to end this seminar. Well, I assure you that this was the most difficult seminar we had in our course. Next one would be somewhat more manageable. And once again, excuse me for making a mistake during the solution of this problem.